Hi, welcome to lecture 7A of our residential technology course. In this lecture, we're going to be looking at building systems. In particular, we're in 7A, we're going to be looking at plumbing and HVAC systems. This is from the chapter in your textbook, which is on building systems, which is chapter 12. So we'll be going through plumbing and HVAC systems in this section. So a little bit about the technology, about how these systems are used in residential construction, and a little bit about coordination, things you got to look at if you're managing these types of projects and how you'd coordinate with the different subcontractors. So we have a hierarchy, and this is your sort of traditional construction hierarchy. Some of you have asked me, what's a hierarchy in a construction project? And this would be a very traditional kind of hierarchy. The client, let's say that the client wants to build a custom home. Well, then they would probably hire a consultant, an architect, to do up the drawings for them and to oversee that the work is actually being done the way they want to have it done if they want to pay that amount. Then they'll usually contract the work out to a general contractor, and that general contractor will pull a bunch of trades together. And in the next few chapters, we're going to continue to talk about the different trades that are involved. In the previous lectures, we looked at like the framing, and we looked at the foundation work, and they would be different trades that would be involved with this. So today we're going to be actually looking at the plumbing and HVAC subcontractors, part of the building systems subcontractors, and they are heavily involved in the process. By the way, this is by no means is a complete list here. It's a long list of subcontractors that you would likely have. Very often you might have 25, 30 different subcontractors on even a house, when you start listing them all out. You might have for the bathroom, you might have a shower door subcontractor that you're going to hire to install the shower doors. You've got your tile subcontractor. You've got your plumbing subcontractor. You've got your drain subcontractor. You've got your HVAC subcontractor. You've got your carpenters doing the finishes, your kitchen supplier and installer. So you've got a lot of different people that are involved in your projects, roofers, sheet metal workers, number of different trades that are involved. And some of them have trades that they hire, depending on how the work is being organized, as you can see. Reporting goes through the line, and it would be reporting to the general contractor. So if I've got a contract, who the contract is between, who reports to who, right? This subcontractor would report to the electrician if this was the setup. Because you want to make sure the lines of communication are clear on a project, and contractually, who are the contracts between? In this case, the owner and the general contractor, the owner and the consultant. So the trades require specific information, and they overlap. Their work crosses each other's. Ducts run, plumbing pipes run, and they get in each other's way. So you have to coordinate the duct runs with the plumbing runs so that there's not problems with that. And the electrical wires. Electrical wiring is a little bit easier to move around compared to the other two. But there's still concerns. You don't want the heating pipes located right above the service panel where all the electrical wiring is going to be coming down. So there's certain things that need to be coordinated to make sure that there's not problems. So scheduling is really an important element of this, and having pre-construction meetings, pre-award meetings with the trades and making sure that everybody's on the same page is very helpful in that regard. Of course, the trades need to interpret the drawings, and there's not a lot on residential drawings, so they have to, in some cases, do their own, as you'll see with the HVAC trade. Plumbing trade has to submit a layout to the city to show how their drain waste vent system is going to be running. So there's a number of other shop-type drawings that are done by the trades as well. So in a larger project, there will be an engineering consultant. So it would be a mechanical engineering consultant that would take care of the plumbing and the HVAC layouts. There would be electrical engineering consultant that would take care of the electrical layouts. They're done on different drawings. Whereas in residential, we tend to put everything kind of on the same drawing, at least from the aspect of the plumbing, like where's the toilet, where's the sink, where's the light switches, what type of light switches are we putting, three-way, is it just a regular switch, is it split switched, all of those kind of bits of information you actually see on the architectural drawings. Whereas a condo building or an institutional building, they'll have a separate electrical layout. Some drawings may have, like for the electrical, a separate layout like you would see in the Brook drawings that came with your textbook, Understanding Construction Drawings for Housing and Small Buildings. So the general contractor needs to facilitate this communication between the trades and coordinate and do it in the best way and most efficient way possible so as not to compromise the various systems. Speaking of compromising the various systems, we have to make sure too, because plumbing trades need to run pipes through joists and your electricians have to drill holes, and HVAC subcontractors have to run duct work. So we have to consider the framing layout, and that's good. That's why you want to have a pre-construction meeting so that if there's any special things that need to be framed for early on, it's a lot easier to do it beforehand than afterwards. Also, you have to comply with the Ontario Building Code or the National Building Code or whatever province that you're in. And so there's requirements around what you can notch and what you can drill. There's very little you can notch in a joist. This is the only real exception. Maximum half the actual joist depth from the edge of the joist. Maximum 1/3 of the actual joist depth, but only on the top. You can only notch on the top. You cannot notch on the bottom of a joist anywhere because it compromises the joist. You can drill up to 1/4 the depth of the joist. So if it's a 2x8 joist, it's not 8 inches, it's 7 1/4. So 1/4 of 7 1/4, you could put a hole that big, but it can't be too close to an edge. So it can't be closer than 2 inches or 50 millimeters from an edge. And the reason for that is that when you think of a joist and you have a load coming down on it, it pushes the joist down. So I want you to imagine that, or take like a pen or a pencil, and when I put a pressure on it, on that pen, what kind of force is on the bottom of the pen? Is it compression or is it tension, right? Force going down. If you said tension, you're right. On the top of the joist, what kind of force would be on it, right? If you said compression, you'd be right. So in the middle, it's more or less neutral. So you don't want to have a hole too close to the top or too close to the bottom because the joist is weakened and it could break at that point. Closest to the middle is the best. Building code just says you have to be 2 inches from an edge, but closest to the middle is the best. So that's important to know because sometimes you'd be surprised what plumbers and electricians will do. You also have to be very careful of manufactured joists because this is for dimensional lumber. Manufactured joists, they actually have more flexibility in a lot of ways, but you've got to follow that manufacturer's requirements. So you got to be very careful of that. For example, if you have LVL beams, a lot of them don't want any holes drilled through the beams. And if they don't want any holes drilled through the beams, you have to plan for that. So just be aware of that, and you can go to any manufacturer's website and they will have basically the guidelines for what you can and you can't do with regards to notching, drilling, etc. From that perspective. But dimensional lumber, we can follow the building code straight off. So it's just exactly what this is. Same with studs, all right? So this is basically a stud. And this is the difference if the stud is on a load-bearing wall or if it's in a non-load-bearing wall. Of course, non-load-bearing wall, you can do a little bit bigger hole because it's not carrying heavy loads on it. Notching, minimum 2/3 the depth. If the stud is load-bearing, has to be left on, so 1/3 that you could notch. Minimum 40 millimeters if it is non-load-bearing, unless the stud is suitably reinforced, and that usually means cutting in a piece and going around it from that perspective. Then non-load bearing, you have more options. So you want to know those things. You want to make sure your plumbers know those things. By the way, here's a quick tip. If you're on a residential site and you're doing this and you're using engineered joists, I would get a printout of, and usually you get copies when they come with the actual shop drawings, and usually you can nail them up on the wall somewhere, all of the hole requirements for this particular system. So your subtrades, they have complete access to it, and they have no excuse and no mistakes, and you're pointing it out to them. It's not something you can necessarily memorize because some systems are different than others. Like 25% of a joist's depth, I have that in my head, right? Those kind of things. Plumber must have knowledge of the plumbing code. So plumbing is a mandatory regulated trade, compulsory regulated trade. So you have to be licensed, and to operate a plumbing business, you have to have a master plumbing license as well. So plumbing code is in the building code. If memory serves me right, it's part 7. Local codes, specifications, structural layout, again, regarding if there's any issues. Because sometimes you run into issues with the layout of the joists and the plumbing and the ductwork. Sometimes that's where you need a bulkhead, so you have to hide a duct or a plumbing pipe that comes below the ceiling. You try to avoid that. Usually it means bulkheads are going to go somewhere, but usually you try to put them if they're going to go somewhere in the basement rather than on the first floor. Or you make it decorative, so you make like a coffered ceiling. If you look at the Brook drawings, I think the dining room has a coffered ceiling all the way around it. That would be a great opportunity to run some ducts and waste pipes if they're problematic in the rooms above. You can kind of make things hidden but look nice. That's a big deal with building systems. Nothing looks worse than just having a bulkhead and then it stops in the middle of a room. Like, what are you thinking? At least bring the bulkhead straight through so it looks clean. So plumbing consists of what we call the DWV. No, in the States they call it DMV, the Department of Motor Vehicles. This is the DWV, the drain waste vent system. So vents are shown on the drawings at dashed lines. So you've come to learn that dashed lines mean hidden lines. In plumbing drawings, they could also mean a vent pipe. So if you see a dashed line and it's a plumbing pipe, it means it's a vent pipe. Plumbers will make isometric drawings of what they're actually doing that they submit to the building department to show how they're going to run the pipes, and in particular the sizing of the drain waste vent system. There's all kinds of rules and regulations in the plumbing code around sizing of vents and location, etc. So they have to be very knowledgeable of the code in that particular area. And the plumbing system overall, the supply system consists of supply lines. We got the drain waste vent system, which is how we get rid of our water and our wastewater. The supply lines are how we bring it into the building. So we got kind of this cycle that comes in, water comes in and water goes out. Going out, it's not as clean as when it came in. When it came in, the term we use is potable water. Potable means drinkable. All right, so remember that. Potable water means drinkable. When we have vertical pipes in water supplies or in heating systems, we call them risers, not just like risers on a stair. So some terms are used interchangeably, but they mean totally different things. So risers in plumbing systems are the vertical supply lines or heating lines if you got hot water heating. A soil stack is a stack pipe that is going to carry waste. So it's going to carry waste from a toilet, right? So that's a soil stack. A stack is a vertical member that carries this discharge. You can have a stack vent, and that might be just the vent above where you got the soil stack. So that's venting out the plumbing system. So we got vent pipes. They ventilate the plumbing system. We have sewer gas in our plumbing systems and in our sewers on the streets, and so it can be like a methane gas, And that gas, if we're not careful, can enter the house. So we have vent pipes that actually vent out through the roof to ensure that that sewer gas goes out of the building. If it comes in the building, it could actually be very harmful to people. Not to mention it smells like crazy, right? So we have in our plumbing system, in our drain waste vent system, mechanisms to ensure that we have that sewer gas go out. So vent pipe is one of those mechanisms. A trap is another, and we'll talk about traps in a minute. But we want to make sure that those are in the system properly. As well, a vent pipe you can kind of think of, it's going to allow your sinks to drain more quickly. It's kind of like a Tetra Pak. You know when you put a straw in it and you suck on it, it's kind of squeezing the box. Well, if you put a hole on the other side, it'll very easily empty itself and it won't be so difficult to pull it. Well, a vent pipe is very much like that hole that you would put on the other side that allows it to vent, and that will allow your sinks and your bathtubs to drain much more quickly and efficiently when they're sized and put in properly. A waste pipe, differing from a soil pipe, a waste pipe carries only the liquid waste, all right, compared to a soil stack, which would carry human waste. So this is basically something from a sink. So it's from a sink or a bathtub as an example, or a basin. A sink is like in a kitchen. A basin is the sink that we have in a bathroom. I used to get lectured all the time from this older plumbing subcontractor that worked with us all the time. George Strawn. You used to always, this is a, Tom, it's not a sink. This is a basin. This is a sink in the kitchen. This is a sink. Okay. So just so you know. Water service, that's the supply line that comes into the house. So we call it the water service. Or the electrical service. That's where the hydro comes into the house, right? So what size is the hydro service? It's a 200 amp service. That's the capacity of your hydro system. The water service is like, what's the size of your water surface? Is it 1/2 inch? Is it 3/4 of an inch? Is it 1 inch? Bigger, you're going to have more pressure in the house. You're not going to have where somebody turns on the shower in one spot and another spot the water goes down. Older houses have 1/2 inch supply lines. And I've got a slide on that in a little bit. So if you're not clear on what I've been talking about, this is the soil stack. It's below the toilet. This is your vent. And this part here would be a wet vent because sometimes you've got the sink discharging water into it. So this vent can sometimes be wet. Generally, when you're flushing the toilet, you're not draining the sink at the same time because somebody's on the toilet, that kind of thing. And I'm calling it a sink again. So the basin, see how I go? Some things never change. The basin. And then we have our vent pipe going up through the top. This is venting the toilet here. And it has to be within so many feet in the plumbing code. So that's why plumbers, they need to know the code really well. Because all of this is going to be inspected under the plumbing permit for the project, and a plumbing inspector will come and inspect the work to make sure it's done properly. And then this goes up, this stack vent, which would be the same size as your soil stack, will go up and through the roof of the house. So it may bend a couple of times, but it's going to go up and through and out the roof of the house. The little round pipe you see going out of people's roofs, that's what that is. And it's ventilating the sewer gas to the outside. This is what we call a P-trap or a water trap. And what that does is it holds water in it so that sewer gas cannot enter into the house. The same thing why when you look at the bottom of a toilet, you see water. There's a trap built into the toilet. All right, so there's a trap built into the toilet. There's a trap built into there's a trap below the basin and below every sink. And there's a trap below the bathtubs and the showers. And there's a trap in the drains in the floor in the basement as well. And that's the protection to stop the sewer gas from coming in. So for example, if you, right now I'm in Collingwood or wherever, and if I don't come up here for a long period of time, well, that water in the traps could evaporate out. In fact, it has. And then I've come up here and it's like the place smells because there's sewer gas in the house, the methane gas from the sewers, and it's really not a nice smell. So the first thing I would run and do is I'd fill the traps with water. All you do is you turn on the sink a little bit, because this water will always stay up to this level, and the excess then goes down and away. So there's your soil stack, there's your waste stack, and this somewhere down below will hook into the soil stack. That's generally what happens. So you have the soil stack, and then it usually hooks into it with that. That's just a different layout. And of course, we have to make sure that our waste pipes are properly sloped. If they are sloped too much, the water runs too quickly away. I won't get into the details what that is, but you get the idea. But it has to have a slope. No slope's not great because it's not going to drain away. One of the inspections that the plumbing inspector does is they check the slope of the drain and make sure that it is moving at the proper speed. So that's part of that. So you can actually have too much. So here is just this pretty good idea giving you sort of like why plumbers learn how to do isometric drawings, so that they can show their plumbing layout, and then they would show the size of the pipes, the drain pipes, 1.5 inches as an example. CO means clean out. That's an access point where they can put a snake into the drain. No, not a real snake. There's those mechanical mechanisms that goes through. You put on the end of the drill, and it can clean out the drains if they become clogged. And it's more like when they become clogged, not if they become clogged. At some point in the lifespan, it will become clogged, and that way you can clean it out, which is very, very helpful. You can also run cameras through the drains, and you can see what the blockage is. You know, you can see all the way out to the street with cameras, and if the drain got broken by tree roots or something like that, you'd be able to see it, which is very, very helpful from that perspective. So the technology is always improving in that way. So you can sort of take a look at it and see any of the dashed lines, that's vents, all right? And then of course the solid lines, that's your drains. And this is representing these particular items here. So toilet, sink, basin, bathtub, toilet, vanity, basin. And here's the vent going through the roof, as I mentioned. Another example for the water supply lines. So the water supply lines come in, you got a cold and hot water line, and they're sized, the cold water, just you have one water line come into the house, it gets separated, and then it will supply the hot water heater. We have hot water tanks. We also have instant hot water heaters too, which can instantly heat the water, which doesn't require it to be held in a tank. Those are supposed to be more energy efficient, because then you're not wasting energy keeping this warm all the time. So there's new technologies. That's not that new. It's been around about 10 years, but essentially that have some advantages and disadvantages too from that perspective. But generally the technology's improved now. It's a pretty good technology, the instant hot water tanks. But they're more expensive, so that's why you typically don't see them in new production homes. For now, they're more expensive. They'll probably be cheaper later on. Here is what I was saying. So here's a 1/2 inch water supply. And you guys are very good at mathematics, so you can just sort of get the drift of this. If you go pi r and you do your calculations for square inches, right, you'll very quickly see that the square inches for this will it's supposed to be pi r squared, so I don't see that it's a squared. It's like, where's pi r? Where's the squared? Pi r squared. It will give you 0.2 square inches, and 3.14 times 0.375 will give you 0.44 square inches. So you go from half, you know, that's just pointing out 1/2 inch diameter pipe to 3/4. Oh, it's not that much bigger. Well, actually it is. It's got more than double the capacity when we talk about area. And area is what's going to allow the water to flow. And you're going to have higher pressure that way in the pipes in the inside of the house, because they would reduce. Some custom homes will have 1 inch diameters, which now you're really getting massive amounts of pressure. So you can look at that, and that kind of tells you the difference between a half-inch water supply. Older houses, like 30, 40 years or more older, they only have a half-inch supply, so from the street. So they will not have the same kind of pressure that more recent houses will have. And that's why somebody turns the shower on in one room, the other room, you're in the shower and you're freezing. Also, houses in the last 30, 40 years, 30 years, will have a TSP, a trap seal primer. So usually in the basement, in the laundry tub, there's a floor drain, and the floor drain has a trap. Well, guess what? Nobody ever puts water in the trap. So that trap will dry out, and then you'll start to smell sewer gas in the basement. So they put a TSP, which means every time it's a special connection to your faucet in the laundry tub, and every time you turn the water on in the laundry tub, a bit of water goes down this pipe and into the trap. So that as long as you're using this laundry tub, once or twice a week, it's going to be sending water into the trap so that it does not dry out. Now, older houses, if you live in an older house, maybe every once in a while it does smell in the basement. Well, what I do is I just get a bucket and I drop the bucket, some of the water into the drain so that it fills up the trap. So if you did that once every 6 weeks or so, or 5 weeks, it will keep water in your drain before it evaporates out. So in some places it might evaporate out quicker than that. It just depends on drafts and things like that in the drain system. But that's another thing. Another thing that helps a lot is modern furnaces that are high efficiency. They have condensation build up in them. And so the condensation is usually got a plastic pipe that goes to the drain, because usually wherever the drain is in modern houses, they put the furnace near the drain, more realistically, they put the drain near the furnace. The furnace should be central to the house, kind of. It makes it much more efficient to deliver it. You don't want the furnace way off in one corner. So it has a condensate drain that they usually just put it above the concrete floor to the drain, and then it constantly puts a little bit of water in the drain too. But TSP is a building code requirement, so that ensures that those drains get filled up. For the drains, we have, I'm just going to put my glasses on so I can see this. So for the drains, we have two systems that we utilize. This is a combined system, and this is a separate system. All right. So a combined system means that you have your clean out and you have your toilets and your sinks, and they're going together and they go into one sanitary sewer, and that's all that's on the street. So in this case, you've got the sanitary sewer, the downspout water, the weeping tile that we talked about in the foundation chapter, all going into the sanitary sewer. Not good, because you got all this excess water. First of all, in the city of Toronto, you've got to disconnect. If you're on a street that this is connected to the sanitary sewer, you've got to disconnect these and run them out on the ground. They don't want all of the water. Imagine you get a torrential downfall. All of the water that comes on the roof goes in the eaves troughs, goes down the downspouts, goes through the drain system and into the public sanitary sewer, which is carrying raw sewage in it. And then it goes to the sewage treatment plant down by the beach. And the sewage treatment plant, well, if you work there and there's a big torrential storm, can you imagine how much water's coming down in those sewer systems? Because the problem is, the city of Toronto was built a long time ago, and when they built it, in lots of the streets there's only one drain, a sanitary drain. There's no storm drain. They're combined. So the only thing they do at the sewage treatment plant when there's a big storm, they open the gates and the raw sewage goes straight into Lake Ontario. Not good. So modern construction methods, we don't do that. We have two systems. So you have for your sewage, and then you have for your stormwater and cleaner water. So then that basically, like your weeping tile and your downspout water and the stormwater from the streets, that goes down in the storm system. That goes into the lake. Well, it's relatively clean water. The sewage water, what we call black water, it goes um, into the sewage treatment plants, and then it's treated before it's let into the lake, so that it's not causing harmful bacteria and other issues. That's why you usually see after a rainfall down by the beach, it'll say no swimming for 48 hours or whatever. They just put up the signs everywhere because they know they opened the gates, and that was the problem. None of the new production homes in that, they're not doing that way when they're building new streets and things like that. But in the older systems, which is a good part of Toronto, that's how it is. In a new house in an old street, you wouldn't do it this way. In a new house in an old street, you would do it this way, and then it would join up to go into the one sewer, because you have no choice because there's still only one sewer, but you keep it separate. So if in, say, 10, 15 years, they come to your street and they put a second sewer line, then they can separate them out, right? And that's part of that process. We looked at a case study in a previous session where we talked about damp proofing a house from the inside, and we showed a sump pump. In this case here, it's showing when it says subsoil drainage connection, it's talking about a connection to the weeping tile. In this particular case, if you've got excess water gathering around the outside house, if you don't have a regular stormwater system to hook up to, rural areas, things of that nature run into that issue, and you're below ground, then your solution is a sump pump. Or if you're in an area where you've got high water tables, again, your solution is to have a sump pump. And so this storm pump, storm sump, which is a sump pump, is basically a hole that's put into the ground, and there's a container that goes around it, and into the container, which is open on the bottom, there's a pump. And as the water rises, as it's fed from the drainage tile around, then it's pumped out beyond the house. So it's basically looking something like this, and then this water is pumped out. A check valve just stops water from backing up as it was pumped out. So that's essentially how that works in that case. And then the best is obviously to get it away from the house. So if you can get it like 10 feet away from the house, that's great. So usually there's some sort of pad that directs it out, or the pipe is laid out along the ground, or there's an extension pipe that's laid onto it, so that the water gets away, because it's kind of pointless to have it come out right here, and it's going to go right back down, and it's going to come out and back in a circle, right? So you want to get it away from the house. That's always the goal, and you always want to have a slope in the ground away from the house as well. So this is the sump pump, which is this right here, which you're looking at. This over here is just showing you a floor drain, FD, with the trap seal primer, also referred to as a TSP. And that's your discharge coming out. So water trap examples that I was mentioning. There's a water trap for a floor drain. This is your water supply line. Because the water supply lines are very often now plastic, they put a tracer line, a piece of wire around it. So in case you ever have to locate it underneath the concrete slab, you can find it with a metal detector. Here is the trap underneath the sinks. This is a connection for a dishwasher here, your cold water, your hot water supply line, cold water, hot water, so cold on the right, hot on the left. And here's a trap for underneath a bathtub. This little pipe that goes up is connecting up with the overflow. So, you know, if the bathtub, you forget to shut it off, it won't go into the room, it'll come down the overflow pipe. And then this pipe over here is your vent pipe coming off of your drain. So you got the trap, your vent going back to probably a wall that'll go vertically up. And here you got your floor drain listed, and there you got your P-trap for your sink, double sink, and this goes back in the wall and down. You can't see that. And then this will be connected with a pipe from the dishwasher, the discharge water from the dishwasher. With these types of plumbing systems and HVAC systems, there's a lot of different things that we use. And so there's very often, we've talked about shop drawings. Well, whoever's making the bathtub, guaranteed there's a shop drawing. It's going to show you the location of the drain, where the drain is going. The plumber needs to know so they can rough it in. They're going to lay out those drains like this based on location from a particular wall so that they make sure that they have the rough in the right spot. Because look, they're drilling through the floor joist to run that pipe through there, right? They want to make sure they put it in the right spot. So they'll have information regarding that. Bathtubs, they're all over the map. Like, they are all over the map. There used to be, like, you know, you had a 5-foot tub and you had a 6-foot tub, and that was about it. And pretty standard stuff. No, you've got to get the shop drawing. You can get it online as long as you know the make and model number of the tub, and that'll usually be listed in the specifications, whatever's been designated. Or you find out what the client's ordering, and then that can be worked out from there. Same with toilets. Toilets are more standard than tubs are. They are generally 12 inches, but there's some makes like Toto toilets and other ones, they may have some particular spacing. So you can't say always, very commonly, but not always. And then it's showing you where you would have from the finished wall to the CL center line of the toilet, where that would be run. So then that would still allow you a little bit of space behind the toilet, and then that would be your location. And you can see here CL of supply. That would be where your water line would come through and out the wall. If this is an outside wall, it won't come through the outside wall. You don't have water supply lines in the outside wall because they'll freeze. It would come up out of the floor in that case, or it could come out of the floor anyways. It just depends. But if it's coming out of the wall, that's an ideal location. Here's basically for a toilet, and this had to be retrofitted after the fact, so that basically the toilet pipe, and then you've got like a double header that they put in here on a joist hanger. They cut this off here. This is cantilevered over the steel beam. It's fine. And the drain pipe, the vent pipe is coming off here. So we have a shower here. We have basically the shower pan. And the pan is just basically a membrane that is put in. There's all kinds of different products. This is probably the most common one, but there's more high scale, upscale products out there for this purpose. Very important if you're managing this process that this is protected so that somebody doesn't, because I don't know what it is, but there's this burning desire that people have to drop drywall screws on this pan and then stand on them, and that cuts the pan, and that means it's going to leak. They're going to put a concrete base in here, but the moisture is still going to go through the leak, and that's when you're going to see stains on the ceiling down below. It's not going to flood, but it's going to leak enough that it's going to cause a problem. So you got to make sure that this pan is protected until the dry concrete is put in, concrete base, and then the ceramic tile is put on, and now it's going to be protected. And of course, this goes up. There's going to be a substrate that's going to go over top of this, probably a cement board or one of the other manufactured type substrates that are waterproof. Not to use a water-resistant drywall. That won't last. It's been done before. It's awful. But you have to use a proper substrate here. HVAC. So that gives us a little bit of an overview of plumbing systems. And now just to give you a bit of an overview of HVAC and sheet metal work. Well, HVAC stands for heating, ventilation, and air conditioning. So again, it's a mandatory regulated trade. It's usually several trades. You're dealing with, usually you'll have your gas license to be able to do gas connections, and you'll have your sheet metal license if you're a sheet metal worker to be able to do all the duct work and connections to the furnace that way. So very often people will have both licenses. If it's a small company, the person's able to do all those things. Then they don't have to have specialty people doing it. But again, furnace repairs and that requires quite a specialized knowledge. And we have to be careful that the furnaces and the gas connections are done right, or the house blows up, and that's not a good thing. You want to make sure that that you have people that are properly licensed. I always remember I was doing an addition on a house one time, and the owner, I don't know what they were doing, but we were doing the addition, very nice guy, the owner, but he was always playing around with the furnace. We weren't doing the furnace, we were just adding addition onto the back, and I remember he was playing around with it, and I was driving home when I left, and on the news came, news bulletin, house blows up at Pape and Danforth, and they named the street right beside Pape, and I was like, what? That was the street and the intersection right where the house was, right where the guy was just playing around with the furnace, right that I knew that he wasn't an HVAC contractor and didn't know really what he was doing. And I thought, oh my God, he blew himself up. So I actually turned around. I was about halfway home. I turned around and I went down there. And surprise, surprise, it was the house across the street that blew up. So never know. But you definitely want to make sure that you have skilled, licensed people that do this work, because that's why it's a mandatory regulated trade. With plumbing, that's why it's a mandatory, compulsory regulated trade. Plumbing, if we mess up the way we install the water supply lines, we could contaminate the water. So you could have contaminated water that's basically sucking water in from the hose outside because it's been not properly installed. So you can have backflow coming in. Sewer gas, the methane gas, if you don't have the proper traps in it, you could have problems with that. So plus, not to mention when you have a leak unexpectedly, it can really do thousands and thousands and thousands of dollars of damage. Now with with HVAC, we have to think about the types of systems, and there's a lot of systems in HVAC systems. So I'm not going to get into all of them. I'm going to explain the most popular one. In the book, it does give a more detailed overview, but you have your supply air, right? And a forced air system is the most popular. Why? Usually these things, it's most popular because it is the most efficient, quick way of doing it. The reason I say that is in Canada, we deal with very cold temperatures and we deal with very warm temperatures, at least in a lot of the locations. And so if you use, say, a hot water heating system, well, then what are you going to do in the summer when you want to air condition the place? Then you got to put ducts in anyways. So rather than put a separate system for hot water and a separate system for air conditioning, you use one system, and the duct system supplies and returns cold air or warm air, depending on whether it's summer or winter. So that's an advantage, but it's not necessarily the most comfortable system. So that's why you'll see on high-end custom homes, they might use a radiant floor heating system, and then they might use a air conditioning system that's using like smaller high-velocity ducts to move the air into the specific rooms to cool those rooms. But it does cost a fair amount more money. So this is the most efficient cost-wise to do that, but not necessarily the most comfortable. Like if you have a radiant floor heating system, it's a very comfortable heat. Even the older houses with hot water heating system, it's a very comfortable heat. Forced air, you get a little bit of drafts with the heat coming out, and in some places it's a little bit uncomfortable with the air moving around. So it's not quite as comfortable, I would say. So hot air, you know it's going to be the hot air, the hot air system or the hot air ducts, what we call the supply ducts, when it comes off the top of the furnace. When it's going to the bottom of the furnace, that's the cold air return. So when we have warm air being heated, it's blown with a blower fan, and that puts enough pressure to move the warm air to the particular rooms where the ducts will come out the floor, the supply air, to heat those rooms. Well, that warm air, It's just basic physics. Warm air rises, it displaces the cooler air, which drops. And the cooler air, if we've got a fan blowing out, we can have that fan also sucking. So basically, when you think of a furnace system, yeah, it's a little bit of a cliche or a joke the way they say it, but it blows and it sucks at the same time. So it's basically displacing and moving the air and drawing back that cold air into the furnace system. So it forms a circulation throughout the house. And it takes advantage of physics, at least with the heating system, that warm air rises. So it's why it doesn't take care of physics so easily when you've got the air conditioner in the summer, because now you got cool air coming off the top and warm air coming down the bottom. And it's harder to get that cool air up to the second floor. So some of you, maybe if you've lived in a 2-story house and you have air conditioning, maybe on hot days, the air conditioner is not powerful enough to get that cool air upstairs, or you have to keep the first floor really cool in order to get the second floor reasonably cool. But in the winter, it works quite fine. So we have that the cold air returns there in that system. So that's our cold air return duct, pulling that air back. And then this is our main supply air duct runs that will have basically the supply lines running off of them. So they all have to be sized. The furnace has to be sized with how much heat, BTUs, British thermal units, it provides, and how do we distribute it to the various rooms? How do we ensure that those rooms actually get it? So we put in things like our return air ducts. And return air ducts, they're not like done like sealed ductwork that supplies the air to the rooms. They're just kind of closed off. So they're not as sealed the way that the supply ones are. Now we tape them and we make sure that they're very sealed tightly. The return air pulls that back down. You're only going to be as good, by the way, you got these big openings here, but smaller openings there. So really this is of the effective opening size. So I don't know if that's exactly sized right the way that they did that. Here we've got an opening. You can sort of see where there's a supply air in the floor there. And they have to do a shop drawing. Well, actually, they have to do for their HVAC permit, they have to do heat loss calculations and drawings. So the heat loss calculations looks at the structure, how thick are the walls, what's the effective R value, how many windows, what direction are they facing, and they enter all this data into a computer software program which calculates the heat loss for the building, which will tell you what size furnace you need. And then the type of blower that the furnace has is also dictating, well, how easy is it going to get that warm air to the various locations. That's why I was saying it's better to have a furnace more centrally located than, say, if I put the furnace back in this corner of the house would be freezing. It'd be very difficult to get the air all the way to this corner. So you want to make sure that it's located in a place where it can at least branch out to the two areas that you're distributing to. And it's actually more than this because there's a room on the second floor over the garage. So it's probably the longest place is probably here. But because of where the steel beam is located and things like that, that also kind of compromises where you locate the furnace. But you definitely wouldn't want to have it in like one corner or the other, even though if you're finishing the basement, that might have been a nice idea. It doesn't work very well with the system. So then basically our duct supply, and this is also saying the size of the duct. So it's a 6-inch duct. It's a 4-inch duct. It's a smaller one in this particular case. And when you see the line going through, that means it's coming out through the top. Where you don't see a line, that's coming in the ceiling. So these two are in the ceiling here. This one's in the ceiling. So it's just going to heat the basement. But these ones, they're going up to the floor above. So this one, I believe, will be in the powder room. This one will be in the front living room. This one will be close to where the kitchen is. This one will be more where the family room is. And that's where you can see them coming out. That's where these ones are coming out, right? That I was just mentioning. The powder room there, there's the powder room. They got them numbered. That's 18, that's 18. That's 12, that's 12. And so then it has to go, these ones are going up to rooms up above. So these ones here have to get ducts as well, like 4, 5, and 6. So there's 4, there's 5, and there's 6. So 6 is coming all the way from there. Usually the room over the garage is the toughest one to heat effectively. So this one actually has, I think, this bedroom and part of this bedroom over the garage, because you have the garage is not conditioned space. So conditioned space means it has heating in it. So because the garage is not conditioned space, it gets cold in the winter, and that can be even though you well insulate, you foam insulate typically the ceilings, or in some of the drawings in the book they've used insulation. It still is difficult to keep those rooms effectively warm in really cold weather. You could compensate with that. You could put a radiant floor heating system in those rooms just to make it nice and comfortable on the feet. If it was a custom home or something along that nature, you might consider that. Also, they have to consider in these plans the fans, the exhaust fans, because that affects the furnace system as well. And with more efficient houses today, and we'll talk about that as well, we use typically an HRV, which is a heat recovery ventilator. I talk about that a little bit more in the next session when we look at the building envelope and what that does. But a heat recovery ventilator allows for fresh air to enter the house and stale air to exit, so that you have a constant source of fresh air in the house. More traditional ways of doing HVAC systems didn't allow for that, but as we build our houses tighter and tighter, we need to have a source of fresh air, an efficient source of fresh air. Just turning the fan on, well, traditionally that would suck in enough fresh air, is not optimal for most designs today. So that's kind of the HVAC systems concept. And here I've got a cut through. This is of the Doncaster house. So if you take a look at the Doncaster house, this is the furnace. And so this is actually this furnace here. This is actually this here. So what's going on here, you see this trunk line going out here. That is that trunk line that's going out there. And that's how that supply duct is getting done and brought over to that point. That's how the supply duct is being brought out over to here. So this is using a BIM drawing, just giving you just a basic concept of how that can be showing where the actual duct layouts are. And we can clearly see, you know, we got to get around the steel beams. So that's got to go around at this point. It's got to go up. It's got to go inside the joist over at this point where the joist changes direction. So there's those kind of considerations that goes on. Usually if ducts are going to be below the ceiling, like I said, you try to do it in the basement. And then if you have issues up above, that's where it's going to require a bulkhead or something similar. So hopefully it gives you an idea of how heating systems work in residential technology, and how plumbing systems, the drain, waste, vent, and the supply systems work in our residential technology. So that's what I wanted to cover today. This is Tom Stephenson signing off, and we will see you in the next lecture, which will look at electrical. Bye for now.